Thank you, everyone, and a very good morning. And it's great to be able to start this talk for this particular group. Yes, so I am here to talk to you about streamlining satellite data for analysis-ready outputs. And a bit of context. They did a great job introducing me, so I don't really have to talk much about myself. I'm Vinayak. I'm a remote sensing engineer. I work for LiveEO, where we are in the new space sector, where we combine the power of satellite data and AI to assist with infrastructure monitoring of different levels. We started in 2018 and have since grown. We have around 120 employees from 30+ countries and offices in four different cities. So a bit of context before I go into how we started streamlining our data. You first need to know why we have the data that we do have. So this is our product suite, where we focus on three major products, which is Treeline, Surface Scout, and TradeAware. And Treeline is where we provide vegetation management for infrastructure such as power lines, railway lines, and the like. Surface Scout, where we detect third-party interference or activity along pipelines. And TradeAware, the newest of our products, where we help with compliance management and detect deforestation as per the new EU deforestation regulations. What all three have in common is that their primary data source is from satellites. So we obtain satellite imagery of different modalities, along with aerial data at times, to run our analytics pipelines. So how does our big data pipeline look like? So we have our data inputs, which typically involve satellite data, the customer data, and any other auxiliary data that might be relevant to that particular product. We have our analytics platform, where we have the data acquisition, harmonization, standardization, the machine learning part, where we do our actual analytics, and then we provide actionable insights to our customers using the web app, mobile app, S3, SAP, or any other delivery format, even zip, RAR, should the customer so want it. What are we going to be focusing in this talk is we'll be focusing on satellite data and how we acquire the data, how we harmonize it using our standardized APIs internally, as well as cloud processing pipelines. So what did we build? This is what we built. I was looking for pictures of combine harvesters, couldn't really find a good 2D picture of a combine harvester, so I did my own. We put in an assortment of different datas from our various providers, such as Planet, Up42, the European Space Agency, USGS, which is the United States governmental body for geospatial surveys. And then it goes into our data acquisition pipeline, and it comes out as haystacks or hay bales, depending on the combine harvester version, which is, in our case, our standardized data. How does this look like? Well, here's a quick overview from a very system contextual view of our end-to-end architecture. Every single block here is representing a whole data pipeline, which is associated with either the acquisition part or the processing part. We also have other pipelines, such as when we get LiDAR data. We have pipelines for georeferencing the images. What does georeferencing mean? For example, a lot of satellite images do not have a context of where they are on Earth. So with georeferencing, what we do is we give it that context on where it actually is on Earth, or give it its sense of coordinate reference systems. All of this is then ingested into our internal database, where then the further teams who actually run the analytics platforms can then access and use as they should. So this is a rough overview of how the acquisition systems of ours look like. The blocks here is common across all acquisition systems for all different sensors that we have. We have our entry point, which is typically through Prefect, where we have our internal operations studio give it the inputs of the area of interest that we are interested in, and then the sensor that we would be interested in for that area of interest. So we query our internal storage, check if some other team has already tried to query images for that particular system, and should they have, then good for us, no money, no extra money, move on. But should that not be the case, then we query something called storage. Now, what is storage? In terms of satellite data, a lot of providers have something called storage, which is technically where we've already have a contract with them for a certain region, which means that, let's say it's Germany, and we have a contract with, let's take Planet. So for example, all images in certain regions in Germany, we can obtain this from Planet for basically no cost because we've already signed a contract with them. This means that we then query storage, which is basically another way of ensuring that we don't incur unnecessary costs should we not want to. Now this data is not available in storage. What do we do next? Then we go query the catalog. Catalog is again a more generic term, but as the name suggests, it's a catalog of data. The data can either be archive data, which means that the provider has already taken those images and is available for sale, or we ask the providers to task the image. Now what does tasking mean? Is technically we send them the area of interest that we would like the images over, and at the next revisit, when the satellite flies over that area of interest, we obtain the images that the satellite has then taken, which is quite fresh. This is usually done due to the varying of seasons and depending on the product. So in certain seasons, we don't really get to see the trees because the leaves have fallen off. So we try to task a lot of these images during the season when the trees do have leaves, which is technically not winter, or depending on the country, never. But once this is obtained, we then submit the order, obtain our images via our internal service, and then we process them, transform the metadata, and then we have a rough item or STAC item, I'll get into that later, of the metadata of what this image is and all other metadata that is required for that image. It is then stored in our database for further processing, which then comes to our pre-processing flows, where we then take the data, and then based on the sensor, we then apply a certain level of operations on it. So these operations vary from sensor to sensor. By sensor, I mean, for example, Pleiades, which is a product from Airbus, or SkySat, which is a product from Planet. So the sensor is technically the satellite system or the camera system that that satellite is using. And every single sensor system requires a different level of standardization that needs to be applied to it. So in certain cases, we would have to go through every single block that you see there, such as updating its no data value, updating the data type for it to be more compatible with our internal machine learning models, applying a QA mask, should that be required, resampling the data, which technically means we either upscale or downscale our images in terms of what the analytics platform would like to do with the image. And then once all of that is done, we put it once more into our internal database. One thing I did skip is stacking bands. So stacking bands is quite important because certain data sources give us their images in different bands. Let's take Sentinel-2, which is from the Copernicus program from the European Space Agency, where they give you around 12 bands for one image. So what we want is all of them merged together. So we just stack all of them into one image, which we can then use. Now, Prefect and Anyscale Ray. How does that fit into our pipeline and what we built? So I'm not sure if anyone here is an art enthusiast and knows what that image is, but that image is by Edwin Landseer, and it has a very cool name, such as Homo proponit, sed Deus disponit, which translates to man proposes, but God disposes. In a very similar fashion, we have Prefect, which orchestrates, and a Ray, which executes. What does that look like? So from a graphical perspective, this is our DAG for our Prefect orchestration pipelines. I will quickly run you through this so that we can move on with the graphs and the diagrams. As mentioned earlier, our entry points, which can vary from CLI arguments for our local in-house testing purposes, API triggers, and schedule runs for the pipelines that are in production. The classic monitoring and artifacts, it is good to monitor and have artifacts when so required. We feature Slack notifications, Prefect artifacts that Prefect natively provides themselves, logging and audit trails for our Anyscale Ray instances. Next comes the configuration layer. Depending on the data, we have different configuration layers. We then also optimize the EC2 instances we use for processing by giving that information into the Anyscale config. So we have the flow parameters, which vary from flow to flow. Flow here would be a data pipeline in Prefect terms. So for example, the A flow which is related to planet would have different input parameters compared to a flow that is related to Pleiades or Pleiades Neo or Sentinel-2. And then we have the information that the pipeline requires next would be about the area of interest or the region of interest, so that we kind of can contextualize what images we actually do need and what we don't need. Once that is done, we have our infrastructure for this, which is the major things to be looking at here is the Ray task runner, which is for our production data pipelines for cloud processing. For local processing, we use the sequential task runner because not all of our systems are that powerful. And then, of course, we have rate limiting so that we don't accidentally cause DDoS attacks. Yes, next. So the task execution layer is something of interest because this is technically where every single task here happens to every single image, where we have different tasks, such as the task where we transform the metadata for this particular image to be standardized for our internal data pipelines. We store them, validate, query. It covers all of these things, and they can all be done asynchronously and parallelly. Then we have our provider orchestration, where, as I showed you earlier, every single provider has their own individual data pipeline. And we have certain processes and tasks that are relevant for certain providers and not for certain others. You can see, for example, SkySat is its own category because of how Planet has set up how the customers will obtain SkySat data. And last but not the least, we have our external systems and APIs that we use, which include our internal APIs for querying our internal databases, as well as the many different APIs that every single provider nowadays has. So we have all of this data, and everything is now stored into our database. How do we ensure that we can give real-time or near real-time analytics to our providers so that we kind of know where the data is, what the data has, and not accidentally take the wrong data? We use STAC. STAC is quite new in the geospatial remote sensing world, but it has become immensely hard to live without. What does STAC stand for? STAC stands for SpatioTemporal Asset Catalog. And it's an open source JSON-based standard to describe geospatial assets. In our case, that would be our satellite data or satellite assets. So they're easy to find, filter, use, and do what you will. What does a STAC database sort of look like? So this is the general view of how our database is sort of designed. We have our imagery catalog, which would then have collections, which would have many collections, and then every single collection would have different items. So what are collections? Collections are user-defined, so you can define your collections to be what you believe would best align with your internal goals. In our case, we have one collection which is just for acquisition. We have another collection which is just for pre-processing, and then we have the third collection which is for every single product to store in data that is relevant only to them. And every single collection, we have items. And in our case, each single item corresponds to a satellite scene. A satellite scene typically means that it is an image taken by the satellite. And along with those items, we have every single auxiliary data that is relevant for that satellite scene. These could range from the data itself to the RPC file, to the IMD, to even just ads from the provider. So it can be whatever they want it to be. What does a STAC item look like? Well, a STAC item looks like that JSON right there on the left. And on the right is what, sorry, I get directionally. On the left is what you see is the footprint, and on the right is the JSON for the STAC item. And when you query your database via the dashboard or an API, you can query the footprint so that then you can align yourself with your internal AOIs to know, yes, this is the image that I'm looking for, without having to scan for too much metadata. The major fields to look at in STAC would be properties, because that's where every single metadata that you find relevant goes into. Next would be assets. So any form of data that you have, this is where you would list them and include metadata that is relevant for that form of data. And this typically means either the href or the location of where the file is, the role of that file, which can range from it being data to it being just an XML with no purpose. And also detailed specifications about the data, such as, for example, in terms of optical imagery, we would have the bands that these images have, which can range from red, green, blue, near infrared, to many more bands in certain cases. This helps us query our database so that we know exactly what we are looking for with the data and whether this is exactly the data that we want to look for. And finally, links, they are used to navigate from individual items. This is typically, internally, we use this mainly to detect pairs. So we use something known as stereo pairs or stereo imagery, where we take an image of a certain locations with 2 different angles or 2 different sensors. The best way to put this forward for people who are not familiar with this would be your eyes. So when you look at an image, you're able to gauge depth based on 2 different eyes. So we have a similar system where using a satellite, you can gain depth information by taking the image of the same location from 2 different angles, which means you have 2 images and you need to relate these images to each other. This is then done using links, where you can see the 4th link right there is a stereo pair. And this is one of the most key factors of why we adopted STAC and why a lot of the people in the remote sensing and geospatial field have moved on to adopt STAC, is the fact that STAC enables extensions, which means that you can design the STAC data or the STAC item which aligns best with what your company's or your personal project's needs are. STAC itself only advocates for the core principles of it, but every single other aspect of it is allowed for extensibility. This is an example of, this is a quick overview, actually, of the different collections that we have internally at LiveEO. So we have, as I mentioned, collection 1, where we store just the raw data. What different types of raw data are stored, that's again based on the modality, which is either optical, elevation, categorical, or SAR, or radar data. And similarly, we have that repeated across our collection 2, where we have pre-processing data, and then collection 3, which is ARD, or analysis-ready data. Here is a example of an analysis-ready data. This is a Pleiades image, where the shaded-in red section is the customer's area of interest. So the customer has certain infrastructure there somewhere in the center of that area of interest, and then our goal is to use this image with our analytics data platform to detect risks to that customer based on the foliage or vegetation that grows within that AOI. So we also clip the image at later stages to just the regions that we are interested in, so that, again, we don't spend too much time processing things that we don't want to. Some quick stats about the pipeline that we've built and what we have at LiveEO. We have integrated over 10+ providers, which means, as you already know, every single provider is its own little bubble. So we had to adapt the pipeline to be able to extensively accept these different providers and then give out a standardized similar item for our end users. We have stored around 45.5 terabytes over the last year in just production, which equals to around 5.2 million items, where the average size of an object is 9.2. And then this is just in the last 2 months, we've ingested around 410,000 items or images into our database. In the last 90 days, we've ingested around 2 million items, and we've grown our database around 13 terabytes. And then coming to Prefect flows, so the volume is that, as you can see, we have around 50% is our acquisition flows, and then around 50% is our standardization flows. The reason why standardization flows are somewhat lesser than our acquisition flows is because of the fact that not every single data source requires us to standardize it for our internal data pipelines. And this is from just from our last 300 runs. The average duration would be around 258 minutes. And you can see that this data is sort of skewed based on the last 300 runs. because of the fact that open source data is our biggest challenge. Open source data is mostly a mess, and having to standardize open source data internally is one of our bigger challenges. So coming to the end, what lessons did we learn over the year and a half when we kind of designed this whole pipeline system? We had to assume provider drift because providers change their APIs and they change their data and layouts. We had to standardize with users, which is internally, where we had to discuss with multiple different teams on what their definition of a standard is, because it's not the easiest, which is a lot of social science, more than data science. Protect the core, because the user asks will conflict, so you have to sort of know when to say no and meet them with adapters instead. So build the core functionality and then enable them to do what they want with adapters. Prove it at scale, which was one of the other major challenges we had in terms of orchestrating with Prefect and executing with Ray, was that when we test, we tend to use around 5 to 6 satellite scenes, but then when we are running it at scale, we have around 300,000 scenes in one particular Prefect flow, which can then cause memory issues or other ways, and having to optimize that is always the key challenge. And yeah, extend standards, don't fork. So when you have open source standards available, you don't have to go for the 96th standard. Just try to extend the current standard rather than trying to define yourself. I believe XKCD had a really good comic about this topic. The current bottlenecks we have is, of course, rate limits, and not internally, but more externally. So our providers tend to have rate limits, and having to implement that into our data pipelines kind of does slow down certain data pipelines when opposed to others. What does this look like? So that is an example Prefect one, and you can see how clearly batched they are. And this is because when we tried running all of them at once, we accidentally DDoSed our provider and got a really stern email from them regarding that. So when we understood, OK, this is the limit that they have set, which is not really clear in the documentation, but it's there now. So that's a bottleneck that we have right now. Yeah, this is the team. We are the people who mainly worked on this over the last year and a half. So thank you to all of them, although they could not be here. And yes, questions?
Hi, so we have an announcement. We do have a questions website that's the same as the talks website. It's videos.pydata-berlin.org. And you can make questions there. You search for this talk, and you can click the green button where we have questions and answers. And we did receive one, and it's about why did you choose Prefect? Can you expand on why you chose Prefect instead of, for example, Airflow?
Yeah, that's a good question, and that's a question I was actually sort of expecting as well, especially with the current state of Airflow and Prefect. So when we first did our transition from, we used to use Airflow a long time ago, and then when we did our transition from Airflow to Prefect, the features and the offers that Prefect had at the time were very much aligned with our company's use cases, which was the major reason why we switched from Prefect to, from Airflow to Prefect. And I believe that Airflow has now since changed how they work. So we are kind of also in negotiation or discussion internally on whether we should switch back or whether we should stay. So that's something that is currently come back up internally as a discussion point. But when the switch did happen, it was majorly because of that. Hopefully that answered your question, whoever asked it. Yes? Nice. OK, perfect.
So any other questions that not from the website?
I was going to write one, but should I just ask it?
Sure.
Yeah. That
Yes.
was a really interesting talk. Thank you. Could you give it? I think I saw that you have a machine learning part of the workflow. Could you give an example of one of the models you're using in that and what the problem is that it's solving?
Yes. So we have quite a few models depending on the data source and the product itself. We also have a very interesting talk which will delve deeper into that on the 3rd by my colleague Ferdi, sitting right there. So we do use foundational models. We've used CNN runners. We have other models, I believe, but I'm not really the ML expert there. Yeah, you can ask him there. Anything to do with the satellite imagery or remote sensing, that's kind of my play area. So, yeah.
Any other questions? We still have 5 minutes.
Yes.
One?
Just checking, you may have said this already, but do you own your own infrastructure, or are you using EC2 instances to run this?
Yes, so the question was whether we own our own infrastructure or we use external infrastructure such as AWS. We currently use AWS, so most of our data is stored on AWS S3, and all of our Ray operations that are executed for our Prefect flows happen on EC2 instances, which are then optimized based on the use case. So which is where we go to in the DAG, somewhere here. Yeah, in the Anyscale config. So in the Anyscale config is where we define which EC2 instance to use for that particular sensor for that particular flow. Certain data sources require more memory optimized flows, and then certain ones require compute optimized. But the majority of them we can just run with M5, certain like very basic metal instances here.
I'm not familiar with Prefect, but does that manage the creation of the instance?
Yes, yeah. So Prefect kind of just creates the instance for the operation. The minute it's done, we then get rid of it. So it's on-spot instances here.
Questions here?
We have 2 more questions on the website. First one is, how is autocorrection or atmospheric correction done in your preprocessing part?
Yes, that's actually a good question and something that is within my work group. So yeah, the atmospheric correction is done in our C1 flow, or depending on the product level that we buy. So for certain products, we buy it after the atmospheric correction is done, so that we don't have to deal with that part and are able to kind of hasten things in our end regarding that. But what we do then is afterwards we correct it based on cloud coverage. I don't know what to look for the question, sorry, at you. But for certain other products, we do atmospheric corrections based on ground sample points that we have and the data that we get from the satellite provider themselves. So they give us information on in the metadata, and then we use that information from the metadata to process those images.
Great. We have another question, is how do you define team boundaries? And if so, how do you communicate between teams effectively?
That's another great question. My colleague there is laughing at that question because, yes, he understands that. So we were, when we were building this, we were something called service teams. So what we did was we had a lot of meetings. That's technically it. Like the best way to communicate this is to sit down with the relevant parties and to talk to them. The most important one would be the one that I have kind of highlighted in the thing, is to have data contracts. Having data contracts really helps, because then you have a contract that 2 people have signed off on in terms of this is exactly what we are looking for. And should they come back to you later and say that that is not what we want, you can just point to them, say that that's what you asked for. But yeah, that does really help, like having something written down somewhere. So just having notes on that would help.
Oh, we do have 2 more questions.
Yeah.
Did you use Ray before Anyscale paid version? How was the change, if applicable? Made it easier maintenance? Is it costly?
We did use Ray before the Anyscale paid version. I mean, we have negotiations directly with Anyscale themselves and with Prefect themselves. So we kind of negotiate contracts with them on how best we can use their services. And in terms of cost, it can be costly, which is one of the major reasons that now that we have built this system, our major focus is on optimizing the system to be more cost efficient.
Thank you. And maybe the last question is, how is it handled when a site location overlaps between 2 tiles?
By this question, Nori, do you mean that it is like the similar AOI, or do you mean that some other team has sort of done this data? But either way, if it is acquiring data that has already been pre-acquired, we have idempotency keys in our stack items. It's not in the sample stack item, unfortunately, but we have keys there where we kind of define that, hey, this data has already been acquired. We have something we call asset IDs as well on a lot of our data, so that we know that this particular image associated with this asset already exists, along with the idempotency key. The key is, it varies depending on which level of processing you're looking at. So it is a very naive UUID when we look at it from just the acquisition part, and then from pre-processing and for the analytical ready databases, we create a hash of every single operation that's run with it, and then we use that hash to sort of generate a new UUID to define that, hey, this particular image has gone through transformation of metadata, it's gone through reprojection, and then it's also been cogified or any such operation.
Yeah, I need the microphone. So thanks a lot for your presentation. And we don't have any time for further questions. So applause for the speaker.